This is the second of the two lectures on Module 4, Turing machines, and we'll continue with some examples. Now, the examples that we did before were right out of the Cornell notes, and I'm going to even simplify those. I'm not going to show the tables showing all of the transitions, but just describe the operation of the machine. And that's the kind of notation that I'm accepting for your homeworks. Okay, so let's let a language be the set of strings that encode a correct addition equation, and let's treat the Turing machine as a language recognizer. And so sample strings in the language would be like this. So we're going to represent numbers as 0, so that's the number 3, and that's the number 2, and I'm separating those numbers with the number 1. So 3 and 2, if I add them together, I would get 5, and so I have 5 zeros, and then finally the end of string marker. So basically that's a correct equation, and what we want to do is have the Turing machine recognize that language. A 0 would be represented with the two ones together, or if it was a 0 here, it would be the start of tape symbol with a 1 with no zeros in between. Okay, so what's the operation? We start at the left-hand side of the string, and we traverse right until the first string is encountered, and then remove it. Now we can shift everybody left if we want to, or we can just keep a blank tape space. It doesn't really matter. We can have a special symbol for blank space if we want, but just remove it. And then what you can do is begin removing. Basically you're going to ask the question, are the numbers of zeros on the left of the remaining one equal to the numbers of zeros on the right of the remaining one? And the way you do that is you go all the way to the left, go to the right one space, and if there's a 0 there, remove it, and go all the way over and remove this first 0. Then go all the way to the left, go back, find the first 0, remove it, go back and remove this 0. So what you're doing is you're removing zeros on each side of that 1 at a time. Well, if they're equal, you should run out of zeros at on either side of that remaining 1 at the same time. So if your final string is this, right, nothing but the start string of 1 and the stop symbol, then answer yes, otherwise no. So we're using the Turing machine as a language recognizer here, and we're asking the question yes or no. By the way, those things are called decision problems. If the answer is yes or no, it's a decision problem, because you're deciding between yes and no. All right, now that's recognizing correct addition, but as we've seen, the Turing machine can actually do calculation. The Cornell notes, we did the +1 for a digital +1. Here I'm going to show just generalized addition, and again I'm going to represent numerals as the number of zeros that you have. And so we have 0, 1, 0, 0, 0, 0, that's 1 plus 4. 0, 0, 0, 1, nothing, that's 3 plus 0. So I'm representing the numbers in a highly inefficient way. I'm representing the numbers simply as the number of zeros that you have. And this is a pretty simple operation. Go to the left, start on the left, go until you find the 1, remove it, and then copy everything to the right of the 1, one space to the left. So when you remove that 1 and copy everything one space to the left, you get a 5. For the second one, you get a 3. For the third one, you get a 4. So we're doing computations here. Now this is such an inefficient representation. It's a very simplistic way of doing math and representing numbers. But as you've seen in the Cornell notes, you can do binary math. You can do this this kind of notation, though, where I'm using this as a way to do representation and highly inefficient, and still talk about the kinds of things we can do. If you have the +1 operator, which we clearly have, you basically have everything in math. But let's convince ourselves, I don't have a slide for it, but let's convince ourselves, say that you can do multiplication. Let's pretend this was, instead of 2 plus 2, it was 2 times 2. What would you do? Well, let's see. I would go from the left. I'd say, okay, there's a 0. I'd go to over to the 1, and there's 2 zeros. And I would put another marker here, and I would copy these 2 zeros to the right of that marker. And then I'd get rid of that 0. All right, so I have a 0, and I'm going to make a copy of that. And then I'm going to see another 0. I'm going to make a copy of that again. And basically what I'm doing is for every 0 that I have in front of the 1, I'm going to make a copy of what's after the 1. Well, that's multiplication. When I'm done, I have to do some cleanup, right? I have to get rid of the original numbers and maybe squish the string together or something like that. But that's what multiplication is. So we can do generalized computations here. Now, let's let things get a little odder here, though. We can't do all problems. Not everything is computable. And we can prove this in a variety of ways. The most common is this. It's a contradiction proof that uses something called diagonalization. So first of all, we're starting out and saying, okay, great. Turing machines can do computation. Now we're saying, but wait a minute, not everything is computable. In other words, not everything can be represented in a Turing machine and be resolved by a Turing machine. And here's how this proof goes. First of all, contradiction proof. We assume all problems are computable. That's how a contradiction proof works. We're just going to assume that a Turing machine can compute everything. If you can encode it, you can compute it. And so let's let that set S be all those Turing machines, M0, M1, M2, M3, and so on and so on. And that would, of course, encompass all the problems. Each Turing machine solves a specific problem. Now, since all the problems are computable, there's no TMs that are not in S. In other words, since all the problems are computable, there must be a Turing machine for all problems, and therefore there's no Turing machines outside of S. Now, let's create a machine that's outside of S. Let's call it M prime. And the way you make M prime is this. Each Turing machine is represented by a string. Now, this is kind of critical. Each Turing machine is represented by a string. Let's talk about that for a minute. You know that table that we made, that the authors made in the Cornell notes? Oops. This table? Isn't that a set of symbols, a sequence of symbols? Couldn't I take this row and then append it with that row, and append it with that row, and append it with that row? And basically what I've got here is a sequence of symbols. A sequence of symbols is called a language, right? Or a set of sequences of symbols. So I basically have a string. A sequence of symbols is a string, so I can represent a Turing machine as a string. Now what do? I let M prime differ from M1 in the first symbol, and then I let M prime differ from M2 in the second symbol, and M prime differ from M3 in the third symbol, and so on and so on. It's called the diagonalization proof because what you're doing, if you had put all of these written all these strings up on the board, one below the other, you're going through the diagonal. The first string you change in the first symbol, the second in the second symbol, the third in the third, the nth in the nth. And what you can determine is that, gosh, M prime must be different from every machine that's in the set. It has to be because it differs from, we made it different from every one of those machines. Therefore, M prime is not in S. Okay, so what does that mean? We assume that all problems are computable by a Turing machine, and then we said, okay, if that's true, there must be a set of all the Turing machines that solves all those problems, and then we prove that, and the statement would say, look, if everything is computable, there's nothing outside of S. All the Turing machines are in S, but then we prove that, wait a minute, there's something not in S. In other words, there's something that a Turing machine can't solve. So now all problems are computable by a Turing machine. Now, this is why I stressed so strongly earlier that there's a strong correlation between a Turing machine and a real-world computer. Even though they behave differently, their capabilities are the same. So what that's saying is not all problems are computable by a computer. Now, we kind of knew that, like the lottery problem, right? We can't predict the future. But what we're saying is there are problems that don't involve that kind of thinking, that a Turing machine can't solve, therefore a computer can't solve. And it's good to recognize that they exist. It's even better to recognize what their characteristics are so that you don't get asked to do things. Well, what is this? What are the characteristics? Why would this work? We've demonstrated that they exist, but what are their characteristics? Why would it be that something isn't computable? Well, when you're going to do a computation, there's an assumption that that computation has an end, right? So the special states halt, yes, no. You have to eventually get to halt, yes or no in order for the computation to be complete, in order for the computation to be valid. So first of all, let's talk about how we have a termination problem. And this first one is, the problems I'm giving here are just a good touchy-feely, not a real proof, just a good intuitive notion. So the robot problem number one, consider an infinitely long wall with a door in it, and you tell the robot to find the door. Well, that's pretty easy. You can think of things that the robot can do. Let's pretend that the wall actually has a beginning at one end, but it's infinitely long on the other end. So on the eastern end, we know where the wall starts, but on the western end, it goes forever. And you tell the robot to find the door. Well, the robot just starts walking, and it will find the door. And that's guaranteed to terminate because there is a door and the robot will find it. But the robot number two, let's change it a little bit. We don't know if there's a door. The wall may have a door in it. Now you ask the robot to go find the door or to determine if the wall has a door. And if the wall has a door, then that will terminate. Right? The robot will find the door. But if the wall doesn't have a door, the robot can never say, no, there is no door. The robot can only say, I haven't found a door yet. So there's no termination. And there are classes of problems that are non-trivial that fall into this domain. For example, let's go back now to languages. We talked about the Mu puzzle earlier in the semester, and the Mu puzzle is an unrestricted language, and the reason it's unrestricted is because you can remove terminals from the string. And so if you're just blindly chugging along with the rules and you're trying to determine if you can solve the Mu puzzle, which was starting with MI, can you derive MU, at what point do you terminate? If you're that robot trying to solve the Mu puzzle, at what point do you say it can't be done? And in languages prior to the unrestricted, so if you talk about the regular language in the context free languages, if you notice, those terminals could never have been removed from the right-hand side of the Backus-Naur form grammars, which means that if you said, hey, is this string in the language? One way to answer that question is to brute force produce all strings of that length, and once you brute force produce all strings of that length, you compare it to the string that was asked of you, and then you can say yes or no. But what if you can make strings shrink and grow? Hey, is this string in the language? It has, in this case, MU only has 2 symbols in it. Is this string in the language? It only has 2 symbols. Well, maybe you have to make the string be 500 symbols long before you can reduce it down to MU. Oh, maybe not. Maybe it's 1,000 long before you reduce it down to MU. Oh, that didn't work. Maybe it's 10,000 long before you reduce it to MU. At what point do you say, gosh, it can't be done? This is why unrestricted grammars introduce a real problem when they say that you cannot, that you can remove the terminals. You can't brute force your result. And guess what? Turing machines correspond to the Backus-Naur form, I'm sorry, to the class of languages known as unrestricted, and the Backus-Naur form grammars that go along with that. So everything's consistent, which is great, right? The grammar and the Turing machine are giving you indications of the same situation. Now these are all touchy-feely, non-proof ways to go about this. What Turing did is he actually did a proof on something called the halting problem. And there's a couple ways to do this, and the author, if you want to follow along in the Cornell notes, you don't have to, does it a slightly different way than I do. I just rely on the diagonalization proof again, which some people do, but it's basically another form of a contradiction proof. And again, let's go to that trick. We know that a Turing machine takes in strings and performs operations based on those strings and gives you a result, assuming the problem is computable. We also know that we can represent a Turing machine by a string. So let's get really weird. Let's make a string representing a TM go as input to another Turing machine. And this has been provably done. Again, the Cornell notes prove it if you want to go through those notes. So you take a Turing machine represent it as a string, feed it into another Turing machine, and now that other Turing machine will act as the first Turing machine. It will simulate the first Turing machine. This may sound weird to you, but you've been doing it for years now. Don't you write software? Don't you write programs? What are you doing? You're taking a program, which is a string, and giving it to the computer, and now the computer simulates your program, or operates on your program. It behaves like your program. So this is just the math model version of programming. A Turing machine is programmable just like a computer is programmable. So we call this the universal Turing machine, and it's the universal Turing machine because it will take in a Turing machine as a string, and then it will simulate that Turing machine. So you give it a Turing machine as a string, you give it another string that represents the problem you wanted the first Turing machine to solve, and the universal Turing machine will act like the first Turing machine and actually solve the problem. And then you start to ask this question. If I give the universal Turing machine this Turing machine and a problem, can the universal Turing machine answer the question, is the original Turing machine guaranteed to halt? Is there termination? And you can ask it in a more general way. I could take the universal Turing machine and just feed it a Turing machine and ask the question, will this Turing machine halt on all possible inputs? So you ask that of the universal Turing machine. And again, it's a decision problem, yes or no. And the problem is that you can't answer the question. It's provably undecidable. So you cannot decide yes or no. And we can do a diagonalization proof on that. Other people do just a straightforward contradiction proof, where if the first machine said yes, the universal Turing machine would say no. Okay, so the halting problem we bring up because it is the canonical problem, and we can map it to a bunch of other problems. All right, so that's the problem Turing used to determine that there are non-computable problems, and to start to get an idea of what those non-computable problems are. Basically, in order for a problem to be decidable, then they require two things. You have to be able to write the algorithm for the problem and guarantee of termination. Writing the algorithm for the problem is often not an issue. Now, again, the lottery problem, that's separate. Predicting the future, we don't have algorithms for that, so they're clearly not computable. But other things, you can write algorithms for it, but then you can't guarantee termination. And so that's really what the Turing machine is coming down to. It's saying that those are the characteristics. You have to be able to write an algorithm for a problem and guarantee termination, and then you've got a computable problem. They don't specify, the Church-Turing thesis, which says that these non-computable problems exist, don't specify specific non-computable problems. Well, I guess other than the halting problem. And we can take the halting problem and map it to a bunch of other things. But this thing to focus on is you have to be able to write an algorithm, guarantee termination. And notice the way that we came to that result. We came to that result by having a Turing machine look at other Turing machines. And what that means in the real world is this. If you want to write software that examines other software and then tells you what that software does, it's an impossible problem. It maps to the halting problem. So if you want to say, I'm going to write a piece of software, and students around the world will thank me forever because my software will look at their software, and if they have an infinite loop, my software will find it and tell them about it. You can't write that software. You can in some specific cases, but in the general case, you can't write that software. Or you say, I'm going to write software that looks at software coming into my computer, and if there's a virus, I will notify the user. Now, think about how that works now. People determine viruses or recognize viruses now by pattern matching, not by analyzing the actions of the software. And so in the general case, it can't be done. That's why we have viruses. If it could be done, we wouldn't have viruses. So that's the big kicker from the whole Turing machine, what is computable, what is not computable. By the way, on the concept of viruses and scanning software, people do try to write software for it, and they're fairly successful because what they're saying is sometimes you can find the answer, like the robot. If you can find the door, then you get the yes answer. So they're saying sometimes you can find the answer, but we're not going to guarantee we can find everything. Okay. And then last, let's talk about interactability just for a minute. Just because something is computable doesn't mean it's still going to work in the real world. There are well-known problems out there that are computable but are not tractable. They tend to be of the form, try every solution. Oh, and by the way, there's so many solutions, it's going to take you a year or 10 years or 1,000 years to get the answer. The algorithm can be written. It's trivial. Try every solution. Termination is guaranteed. Try every solution. The problem is it just takes way too long. And if you remember your order notation from CS315 or CS222, these are the problems that are order n to the k. The size of the problem raised to a power, like n squared is typical, or n factorial. And when I talk about too long, it's not about getting a faster computer. This is really, this thing takes centuries. So we have things like the traveling salesman problem, bin packing problem, graph coloring. You can Google those, and people have studied those a lot. You can look for those. But these are problems that are technically Turing computable, but in practice simply take too long. So they're not considered practically computable. Okay, that's the module. After this, I think we're going to move back into the real world and talk more about programming and compilation, which follows directly from the grammar stuff that we've been talking about.